So in order to do the extra credit to find the frequency of energy of the waves of light that you saw in the flame test, you're going to need to have a few pieces of information before you do that. So we're going to look at the equations and the constants that you're going to be using. So the first constant that you're going to use is represented by the letter C, and it represents the speed of light. And that value is 3.0 times 10 to the 8th meters per second. So light travels at this speed. So in 1 second, light can travel 3.0 times 10 to the 8th meters. The next constant that you're going to need to use is Planck's constant, and it is 6.626. So this is written a little bit incorrect here. So 6.626 is actually the value, so not what is written here. So write down what's in red. 6.626 times 10 to the negative 34th joules times seconds. So it's not a division sign there. You're also going to want to know what units things are going to need to be in. So your energy is going to be represented by the letter E, and the unit on that is going to be joules, which is represented by a J. You're also going to be using a V in one of your equations. That V represents hertz, so that's what our unit is going to be for frequency. And hertz can also be written as 1 over seconds, and we'll see where that comes into play when we do an example problem here. The next one is lambda, so that is what this symbol here is. It's a Greek symbol, and that represents the wavelength, and that unit is going to need to be in meters. And then the two equations we're going to use. The speed of light equals the wavelength times the frequency, and energy equals Planck's constant times the frequency. So those are the two equations that we'll be using as we go through this. Now, before we can plug our values into the equations, we need to convert our nanometers into meters, because if you remember, the speed of light is written in meters per second, so we need for our length of the waves to be in meters in order for those units to work out. So 1 nanometer is equal to 1.0 times 10 to the negative 9th meters. So your nanometers for your different wavelengths that you found in the table in your lab handout, you're going to be using those values, not the one that I have here. But here's our example. So if we have a wave that has a wavelength of 500 nanometers, we need to convert it into meters. We're going to do it just like this. So we have 500 nanometers. And we're going to set up an equivalent statement. So we already have our statement here. In order for my nanometers to cancel, it must be on the bottom. So 1 nanometer is here. And then on the top is 1.0 times 10 to the negative 9th meters. So this is not a cross multiply and divide situation. This is a multiply across situation and then divide. So we're going to do 500 nanometers, and you're going to multiply that by 1.0 times 10 to the negative 9th, our value right here. And then you just divide by 1, so it's going to give you the same value. When you put this in your calculator, you should get 5.0 times 10 to the negative 7th, and our units on that will be meters. And that's because my nanometers are going to cancel out. If you are not getting this value, particularly if your exponent here is incorrect, that means that you're typing it into the calculator wrong. So if you just stop and see me, I can show you how to correctly put that into your calculator. But even if you are getting that value incorrect, still watch the rest of this so we're able to plug those numbers in once we get that value for the wavelength. So first one that we're going to do, we're going to find frequency here. So the wavelength of a wave is 2.0 times 10 to the negative 5th meters. So go ahead and do this as a practice problem, then you'll be able to plug your wavelengths in. So we're looking for the frequency. So this is the first thing that you have to find for part of your extra credit is the frequency. So looking at the equations that we have, we are going to use the one that has wavelength and frequency and the speed of light. So really what we're doing is some simple algebra. We have two things that we know. We know the speed of light and we know the wavelength at this point, and we're just solving for the unknown. So if you go back to that constants page that we started with, C equals 3.0 times 10 to the 8th meters per second. So 3.0 times 10 to the 8th, that's an 8 meters per second equals, now we're going to insert our wavelength, 2.0 times 10 to the negative 5th meters, and we're multiplying that by our frequency. So we're just going to rearrange this equation. So if we divide each side by the 2.0 times 10 to the negative 5th meters, what you should be left with is 1.499 times 10 to the not negative, 10 to the 13th. And we're left with 1 over seconds. So let's look at how we got that. When we divided this over, my meters canceled. So now there's nothing here, which leaves it as a 1. So 1 over second. But if you remember on the first video, or the first slide rather, that 1 over seconds is the same thing as hertz. So you're going to want to rewrite that as being in hertz for your frequency. So once again, if you are not getting this value when you are typing this in your calculator, it means that you're typing something into your calculator incorrectly. And we can fix that really quickly if you just come see me and I can show you what way to turn that in. Particularly, it's going to be that exponent that's probably going to be wrong if you're missing anything. Alright, so frequency is the first thing you have to find. The next thing that you have to find is energy. Now, you need to have the frequency in order to be able to find the energy, so we're going to find the frequency of all of those waves first, and then we're going to find the energy. So anytime we're looking for energy, we're going to use the equation of energy equals HV. So remember that H is that Planck's constant, so you can check the value of that. And then we have the frequency. So you are going to plug in the frequency that you find for each of your waves into this equation. This value is not the same. But let's take a look at this problem here. So E equals, remember Planck's constant was 6.626 times 10 to the negative 34th joules times seconds, and we are multiplying that by, I'm going to have to go on to the next row here probably, 5.76 times 10 to the 14th hertz, which if you remember is the same thing as 1 over seconds. So then we just do a straight multiplication. 6.626 times 10 to the negative 34th in your calculator. Multiply that by 5.76 times 10 to the 14th. And what we should get is 3.82 times 10, to the negative 19th. And we are going to be left with joules as our energy. So what you're going to do these same steps with your wavelengths that you found for your different colors of light for the samples that we did in lab. As always, if you have any questions, please let me know.